Okay. Y'all are very quiet. All right, so the first homework, or second homework, should have gotten that done by 9 a.m. this morning. So I just posted the next homework, which is due next Tuesday at 5 p.m. So, and then I'm going to actually, after Monday's class, I'll release number 4. It will also be due at Tuesday at 5 p.m. So don't wait till the last minute for this. This is a long one, and there's going to be more due at that time. So get going soon. Okay, and you can. After today's class, there's lots you can work on this homework. And then the 18th is our first exam. So a week from today is our first exam. And we will not meet here because you're going to have 90 minutes to complete the exam. So we'll have another classroom. You can either come a half an hour before class and have 90 minutes, or you can start at the beginning of class and have 90 minutes. So hopefully you're either free before class for half an hour or after class for half an hour. And then so there'll be like kind of 2 waves coming in to do that. And then if not, then we'll make arrangements for you. Okay, so if you're booked, you cannot clear your schedule before and after class. If that's you, then we'll make arrangements. Okay. So more about the test, but it is a week from today, and I will announce the other classroom and that whole procedure again on Friday or soon. Okay, it'll be on announcements on Canvas. Any questions about that stuff? Okay, so we're working on volumes, and we were working on this example. We said, so I can show you these really pretty animations and graphics up here to help you understand what's going on, and that's great. But when it comes to you doing the problems, you're going to be staring at a block of text, and you're going to have to come up with some sketches. So we're going to practice that in class as well. So we'll start with this. So can you sketch what the empty shell that you'll get if you rotate this around the x-axis? Try that. Can you come up with some kind of sketch of the empty shell that you would get when you sketch that curve? This is sine x from 0 to pi. When you sketch that around the x-axis, can you make some kind of sketch of the empty shell that you would get? And then while you're at it, the empty shell you'd get if you rotate that around the y-axis, so both of them. So what shell would you get if you rotate it around the x, and what shell would you get when you rotate it around the y? See if you can draw both those pictures. So the artistry does not have to be perfect. It's not about perfection, but it's just about getting something good enough that you have the right mental image of what it is. Okay, so for the first one around the x-axis, did you get something like that? So it doesn't have to look just like mine. It doesn't have to be perfect, but it has to be good enough so that when you look at your picture, your image of it is that, right? Do you have the right image of it? So you're conceptualizing it correctly. Okay, what about this one? So what are we going to call this shape? It looks like what? Let's call it a football, okay? And then this one, so notice what I did. I kind of redrew that. I redrew that shape. This is one technique. I redrew that shape like every 90 degrees. So 4 times. I drew it at the bottom after going through 180 degrees. I drew it here. That's kind of like the front, and that's like the back. So this is one technique for helping you sketch these 3D images. It's like re-sketch this 3 times where it would go like every 90 degrees. So we can do that same thing here. So here, so something like this. Let's try a little bit better than that. Okay, that's better. All right, so that's like when it's rotated 180. And so then what's going to happen? This is going to form a circle. And then back there. So this is like the bottom circle of it. something like that. And then I can draw that same thing again, like here, like here. And then I could draw that right there. And this would be dark. So you'd be able to see. And what are we going to call this? What is this like? It's not really a donut because it doesn't have a hole. Bunt cake? Is it kind of like a bunt cake? You guys know what that is? The first class knew what a bunt cake is. You guys know what a bunt cake is? Let's go with that. You can Google it, right? Google anything. All right, so it's a bunt cake, but it doesn't have the hole. Or what's the? There's some kind of like bread roll that this is like. What's it called? No. What is it called? A bialy? A bialy? Is that what it's called? Something like that? Yeah, right. What? Yeah. Your teacher's crazy. Okay. All right, so we'll go with bunt cake. So football and bunt cake. All right. Did your sketch end up something like this? That's what we want. Okay. Again here, so let's actually look at the pretty one now. So we got the pretty one. Oh, that's the other one. That's the bunt cake. And then this one is the football. All right, so these are the empty shells that we're going to fill up, right? So the idea behind these volumes is we're going to create the empty shell. Somehow with a curve, we're going to create the empty shell, usually by rotating. Okay, well, you'll see in recitation tomorrow there's other ways to do it, but usually by rotating, you'll form an empty shell, and then we're going to fill the shell with cylinders and track the amount of volume that's accumulated in those cylinders as we go. And then when we get the whole thing filled up, we'll have the volume of the whole thing, right? So when we get the whole thing filled up with cylinders, then we'll track the total volume. Okay, so that's kind of the game plan here, and we want to practice our sketches. So what did we do last time? We did this one, right? This gray one here. So let's look at that. And what did we say? We're going to start with delta x intervals, and we're going to let the cylinders form in delta x intervals to fill up the shell. And so we looked at this last time, right? And so if we want accumulation of volume, what do we need? So the quantity that's in question now is volume, and if we want to write an accumulation of volume function, we need what? Rate of change of volume. That's what you should be thinking. This is the big theme, that if in the first week, we developed this way to write an accumulation function for any quantity. And what we need to do that is the rate of change of that quantity. So now we're talking about volume. If we want to write the accumulation of volume, we need the rate of change of volume. And so then at last class, we worked on two different ways these cylinders can grow, or how they can vary, these cylinders. And then we got a rate of change function for each way that they could vary. So what were the two ways they could vary? Cylinders could vary in radius and height. And when they varied in radius, we found the rate of change function for that. And then when they varied in height, we found the rate of change function. So then the question is for this one, are these cylinders varying in radius or in height? So the key is don't compare cylinders. That's the key. You're just looking at how a particular cylinder, or the current cylinder in the current interval, how it changes, how its dimensions change. So you're focusing on the purple one. Is it showing up purple? Yeah. You focus on the purple one, right? In the current interval, how does the purple one vary? In radius or in height? Okay, you should be thinking in height. And let me show you even a different way here. So instead of... So let's not keep the ones that we've seen before. We'll just focus on the current one. So this is always in the current interval now. The cylinder growing as x varies through the delta x interval, right? So do you see that each of those cylinders is increasing in height with a constant radius. That's what you need to see, because that's going to determine what our rate of change function is. And did we write it down? I think we hurried at the end and wrote it down, but let's do it again. So if they vary in height, what did we come up with for the rate of change? So the rate of change of volume, so cylinders vary in height, then the rate of change of volume is? Just in general, do you remember what we said? Area of the base, right? Area of the base. Or that black face, right? It's the leading face, or where the volume is accumulating. The place where the volume is accumulating, the size of that is the rate of change. So where's the volume accumulating? It's accumulating on the right face of every one of these the cylinders. That's where the volume's accumulating. That black face. That's where the accumulation is happening. So the magnitude or the size of that black face is going to be the rate of change of volume. So that's the area of the base. That's the area of the base of that cylinder. Even though it's standing up on end, it's still the base. And the radius is up and down now. Does that make sense? So that's the area of the base. So what is the area of the base? What kind of region is it? Pi r squared. It's a circle. No hole here, so it's easy. Pi r squared. Easier than without the hole. So just pi r squared. So now we got to get the radius in terms of x. So we can draw a typical cylinder here. So that's the radius right there. So what is the radius? So this is the question. When we're trying to find the radii and heights of these cylinders, here's the questions we're going to ask. Is it the x-coordinate? Is it the y-coordinate? Is it a big change in x or a big change in y? It's always going to be one of those four things. Is it the x-coordinate, the y-coordinate, a big change in x, or a big change in y? That radius. Y-coordinate. It's just the y-coordinate of our, right? Because from the x-axis up to the curve, so it's the y-coordinate. So I can rewrite this radius as, or this area of the base as, pi y squared. But what's our independent variable? X is increasing through delta x intervals. So we need, and this was our rate of change function needs to be in terms of our independent variable x. So does this. So pi times, we need y in terms of x. So what is y in terms of x? That's the curve sine x. So now we've got the rate of change in terms of x, and we can write the volume accumulation function. All the volume up to 0 plus, right? This is our standard form for our total accumulation, 0 to x of the rate of change times dt, right? That whole thing, what is that? Constant rate of change. Rate times little change, like m dx, right? M dx. And we're accumulating or summing up all those little changes to get all the accumulation up to x. What is v of 0? Yes, how much volume I have accumulated already at 0. And how much is that? Here's x equals 0. How much volume has been accumulated already? 0, none. So this can go away. We don't really need it. And so in this case, the net accumulation starting at 0 is the same as the total accumulation starting from 0 because there's nothing from before. There's nothing to add on from before. So we got it. Okay, and I'm going to call that V1. V1 is when we rotate around the x-axis. So I'm going to put that in. Let's put that in here. So questions on what I did while I type this in? Anybody have a question? So integral is, and GC is Control-Shift-I, Control-Shift-I. And then you can change everything that you need to there. So we got pi sine t squared dt. Okay, is that what we said? So there's our volume accumulation function for the football. So we rotated about the x-axis, x varied through delta x intervals, and made a football shell. And the cylinders were like, we'll call these like discs, right? Discs. Or I might use pancakes sometimes. Discs or pancakes. That's what the cylinders become like. Now, the fact that we're using integral means that so I'm showing in this animation, I'm showing that the delta x intervals are big. But when we get to, so writing it as the integral means the delta x intervals are super small, right? And what happens when the delta x intervals are super small? You see how the cylinders aren't really perfectly filling the shell, matching it perfectly, right? Because it's like, this is our approximate situation with kind of large, not small delta x. When delta x gets super, super small, you know that the pancakes are like crepes. They're like super thin. And then they fill when they're small enough, they fill the shell perfectly, right? That's integral, okay? That's integral. When those pancakes are super, super thin, like just like flat circle discs, okay? They'll fill up the shell perfectly, and that's what this represents. The picture I'm showing is more an approximation situation for not small delta x. Okay, what about the other one? So now in this one, we drew the bundt cake. Okay, so now delta x varying through. So let's go back here. I want to show you how to do this. All right, so if I have this situation and I say, I want to fill this empty shell with cylinders for the independent variable being x, then here's the way we do that. We break up the x-axis into delta x intervals like this. Each one of those is delta x interval, and then we imagine a kind of like a strip. So this is just in the surface, right? So just okay. So imagine a strip whose left side is the height of the function, and then it stays constant. And then to get the cylinder that we're going to get is we take that strip and we rotate it about the axis just like we rotated the curve about the axis. So what are you going to get when you rotate that strip in a delta x interval? When you rotate that around the y-axis, what are you going to get? So over. So about the same size on the other side. So when it gets halfway, it's going to be there, and so then it's going to rotate around like this. Okay, so that's like the typical kind of cylinder we're going to get for this shell if we let x vary through delta x intervals. So you start with a delta x interval, draw a strip, and then imagine that strip rotating the same way that the curve rotated. And then what you get from that is going to be the kind of the type of cylinder that we have. Okay, so now I'll show you the pretty version. So do you see? So now this is each cylinder growing in the current interval. All right, and so then if we want the accumulation of volume, we need, what do we need to get right accumulation of volume? Rate of change of volume. So to determine the rate of change, we have to ask, are those cylinders growing in height, or are they growing in radius?
Radius.
Good. In chorus, you said radius. Excellent. Yes, their heights are different, but don't compare cylinders. Look at how each one grows, each one increases, how each one accumulates volume. Each one accumulates volume by growing in radius. Okay? So we then, therefore, the rate of change of volume in this case, with respect to x, is when they grow in radius. Remember what we derived last time? So it's the size, the magnitude of the thing that's growing, right? So this is now this circular side. And what's the area of that? 2 pi RH. Right? So it's each one is growing. This is the part that's growing. The radius is growing. So this is that size of that face, that leading edge, or that where the accumulation is happening, right? The size of that is the rate of change. So that's the 2 pi RH. And now we're doing it in terms of x, so we need to get r and h in terms of x. So we need the radius, and we need the height. And for each of those, we're going to ask the question, is it an x-coordinate, is it a y-coordinate, is it a big change in x, or a big change in y? So the radius, x, y, big change in x, big change in y. X-coordinate, good. It's the distance from the y-axis to the right. That's the x-coordinate. Height. It's the y value. So our rate of change is 2 pi xy, but we need to get the whole thing in terms of x, so we're going to leave the x is fine. The y needs to change, so what is the function, which is the same function as before? Sine x. So we got 2 pi x sine x. Yes, please.
Is y always going to be sine x?
No. So we can create all kinds of different volumes from different curves. This is the example we've been working on. So you got every curve that you've ever seen in pre-calculus and calculus can be rotated around different things to form all kinds of different empty shells. Does that make sense? What's that?
It'll always be the function of y.
No, because we could rotate. So don't look for this will always be that, and this situation will always yield this. So come to every problem and do them all separately, because if you try to start generalizing and like making categories, you'll find one that doesn't fit your categories, and then you'll be in trouble. So just do every problem separately and analyze. Like build it from scratch every time. Yeah.
Are there any situations where we can't find a volume?
I don't understand your question. Like,
There's a dumb question in mind.
well, I mean, I just don't know. I guess I don't know what you're asking.
Oh, forget. I need words.
Yeah. So just well, maybe we'll talk about it later. What's that?
It's not just a surface area.
What's that?
2 pi RH, how do we get that?
That's what we derived last time in class. When the radius is growing, the rate of change is the size of the space that's growing. That's what we derived in class last time. Do you remember that? So how are these shells are growing in radius, and so the leading face or the leading edge is this circular side that's expanding, right? So we said that was the big theme last time, that the rate of change is that magnitude of that thing where the accumulation is happening. So that's the 2 pi RH is the area of the black circular side. And that's the rate of change. Okay, so now we can write our accumulation function. I'm just going to write to the GC file. it be? So I'll call this V2 now. Control Shift I. Okay, so our volume accumulation for the bundt cake, filling up the bundt cake, is 0 to of 2 pi x sine x. What about we want sine? We want t's in here. They are x values, but we need a different symbol because it's going to be every x value from 0 to x. So there we got it. All right, so now I want to, so we've got, let's start with this one. So we filled that thing up. And I want to know what's the volume of the whole football. So how can I find out what the volume of the entire solid football is? So pretend those intervals are super small, and we have this perfect situation of filling up that thing all the way. How much volume is that? How am I going to get it? GC is your friend. Nope, GC is your friend. What do I need to type? It's about 3 or 4 keystrokes. And it'll tell me the volume of the whole thing, yes? She wants V1 of pi. Yeah, that's it. Good job. V1. Why V1 of pi? What? Because function notation gives us a value of the dependent variable. In this case, the function notation can give us values of volume for given x values, right? Based on this function, for given x values, we can get the value of the function. And we want it at pi. If we want the whole thing filled up, then we want it all the way x all the way to pi. Does that make sense? Okay, now I want to represent half of that volume. How can I represent half of that volume? So V1 of pi over 2. And when you say over 2, what's over 2? Pi? Like this? Is that half of the volume? Is there another way? So you're suggesting?
That we do v sub 1 of pi.
Yeah?
That over 2.
The whole thing over 2. Which one do you trust more? Which one would you trust if I was asking for half of the total volume? Which one would you trust? The first one or the second one? Second one, right? So you just take the number and divide by 2, right? Now, what is V1 of pi over 2? What does that mean? Yeah, that's when we're halfway done filling this thing with cylinders. And what happens when we're halfway done filling it with cylinders? So x is only out to pi over 2, so it's just this much of it, right? And what happens when we're halfway done with x? Do we get half the volume? I mean, you're looking at it, right? We do, right? So when you accumulate up to halfway in x, you do get half of the volume, right? You do get half of the volume. So they both give you half, but this was the one we know for sure will, okay? So let's look at the other one. So the other one, this one. I want the volume of the whole thing. So what should I type in to get the volume of the whole bundt cake? How much is there to eat? What should I type? V sub 2. Use function notation, right? Use function notation of I want the whole volume. Pi again, right? So, because we want that whole thing filled. Remember what they look like? They're like sleeves. Each sleeve was around the ones before. So we went all those sleeves all the way out to pi. And so the bundt cake, a lot more stuff, or takes up a lot more room than the football, right? 4 times as much or something. Okay, now I want to get half of the volume. What should I put to do half of the volume? The whole thing over 2, and it looks about right, 19.7. About half of that, like 9.8 or 9.9, to get half of that. So what about if I accumulate 2 pi over 2 here? Will I get half of the volume? Oops. I just want to accumulate to this much, right? So just accumulating just the amount of volume accumulated when I get to halfway, pi over 2. Will that be half the volume? Less or more? Good. You see that's less, because all these points, if I rotate them around, have a lot, they don't have nearly as far to go, right, as all these points out here. So all these points out here, yes, this area is the same as this area, but all these points, when you rotate them around, are going to have a lot farther distance to go and create a lot more volume. Do you see that? But these in here, they're going to create less volume because they have a shorter distance to go around. So when we do v2 of pi over 2, we should see something less than 9.8. 6.28. It ends up being 2 pi. That's just coincidence. Okay, does that make sense? So because of the symmetry of the football, accumulating halfway out in x does give you half the volume, but not with the bundt cake. Accumulating halfway out in x actually gives you less than half of the volume because of this thing I explained before, but how all these points go a shorter distance than all these points out here. Okay, but emphasizing that we're going to set up these accumulation functions in GC, and then we're going to use function notation to calculate the values, the actual values that we want. That's our thing in this first part of the course. Write the correct accumulation function, and then just type the right function notation, and it'll crank out values of accumulation that we want. Okay, so let's move on to the worksheet example. Unless there's questions about this example. Okay, so in this, yes, are there extras in the back? Okay, so here's this worksheet, and so now we're going to take this function, it's just f of x, as far as we know, it's just f of x, out to 1, and we're going to rotate this around the y-axis to make a shell. And so on the first image, we're going to practice here. First image, we're going to try to sketch the empty shell that you'll get. All right, so it's below f of x, less than 1, and y greater than 0. So this is x equals 1. This is y equals 0. This is f. So don't draw all that. Don't draw all that. I'm just showing you what the region is. That's the region that you want to rotate. So on this first sketch, rather than what I did, you're going to sketch the empty shell that you get when you rotate this thing right here, around the y-axis. The y-axis. Try to sketch the empty shell. Visualize it and imagine it correctly, not draw it perfectly. So if you're not a good artist, that's okay. It's just as long as you can have the right visual in your mind. So does your picture look like this, or is that what you're imagining from your picture? That's the key. Okay, so what are we filling up? What's the empty shell that we're filling up? Are we filling up inside the bowl? Are we filling up kind of underneath the bowl and leaving the bowl empty. So underneath, right? So this is the inside of the shark fin was our region. So when we rotate that around, then the empty shell is like inside the shark fin rotated around, so it's underneath the bowl is what we're filling up. The bowl's going to stay empty, and we're going to fill up the part underneath the bowl. So that like in the end, we have like a football stand, right? So like we have a solid, this will all be solid in here, and it could hold the football if we stuck the football in there, okay? That's what we're after. So how do we do this? So now, so that's we did that. So now we're going to make intervals, delta x of 0.2 along the x-axis. And then we want to sketch a cylinder in the delta x interval starting from 0.6. Okay, but not the whole width of the interval, just like we imagine that x is increasing starting from 0.6 and the cylinder is increasing. And so somewhere in that interval you're going to throw x in there. Not all the way to 0.8, but somewhere between 0.6 and 0.8. And so your cylinder, its inner radius is a value of x. That would be the 0.6. The outer radius is the value of x, so that's varying in the interval. So you're going to just pick a spot somewhere in the interval. The height is the value of f of x at the beginning of the interval. So the height stays constant. And then that's it. So that's what we're doing now. In the second drawing, we're doing this much. Part B. So the goal is, can you draw the typical cylinder in the current x interval if the current x interval is at 0.6? So you're going to first mark the intervals of 0.2, and then draw the cylinder in the fourth interval, which is the one starting at 0.6. See how it goes. Go for it. Okay, so you start with a strip. So inner radius 0.6, outer radius x. X is varying in that interval, right? X is growing. So the cylinder grows, right? And then to draw that cylinder, then you're going to draw the mirror image over here. And then imagine what would that cylinder look like if that thing was rotated around, just like the curve was rotated around. Did you draw something like that? So this is the cylinder in the current x interval. Any questions? Okay, so we're ready to write the volumes. Once we've got the typical cylinder in the current x interval, we're going to write rate of change of volume. And what's the rate of change going to be? So the rate of change depends on how these cylinders vary in the current interval. What varies in the current interval? The height or the radius?
Radius.
Good, radius. X is changing, right? X is changing. As x changes, the radius grows. And the height stays constant. So when the radius is growing, our rate of change is 2 pi RH. So the radius is x, y, change in x or change in y? X. This turns out to have the same features as the previous one. height is y, and that is f of x. I didn't tell you what it was. So we're going to call it f of x. And then we can write the volume accumulation. And we use function notation, right? I defined what the rate function was over there, r sub v. So now I'm just going to use r sub v of t. Perfectly, that's what function notation does, right? Stands for the dependent value of the function. So I can just use rv of t, knowing that rv of x is my 2 pi x f of x. Okay, so now we need the other situation at the bottom of the page there. Any questions on that? So the second half of the page, now it's going to be the same empty shell. The same empty shell, but now we're going to let y vary through delta y intervals. So we're going to start with intervals of 0.2, and then for the interval of 0.4, we're going to sketch the cylinder that's growing in the interval from 0.4 to 0.6. You don't have to sketch the empty shell again, it's the same one. So it's the same empty shell, but now we're going to let y vary through delta y intervals. So you're going to sketch off the delta y intervals, and then sketch the cylinder in the third interval, the one that starts at 0.4. Go. That's what those instructions should say in the bottom half. Sketch off delta y intervals of 0.2, and then sketch the cylinder you'll get for that. Okay, so the part that gets filled up is underneath the curve, right? So these cylinders are filling that up. So the strip you want is in the part that's getting filled up. So you want your strip there, and then you're going to rotate your strip around the y-axis till it's over here. And then imagine the cylinder you get when you rotate all the way around. Can you imagine the cylinder that you'll get? It kind of gets a little messy when you do this, so I'll do my best. I won't draw it with any thickness, I'll just do those two circles. Okay, so that's the kind of cylinder we're going to get, but imagine it has this thickness the whole way around. Yeah?
For the rectangle, is it supposed to be going inside of the shell? Like
Yeah, it is, right? This is the shell in here. So
I
you're...
meant the hollow part, like how you have that little edge inside of.
Yeah, so it's going to keep the same inner radius for the whole interval. So whatever that value is there, it's going to be vertical. Yep, it's going to be vertical there. So then just a better view of this is like this. Okay, so this hole, what is this hole for? This hole is for like the bowl, the open bowl, right? So there we go. Okay, so this is just the current interval. It's not leaving the cylinders behind. It should, as we accumulate volume, it should leave all the completed ones behind, right? So that it's accumulating from bottom to top. So we ask for these cylinders, what is varying? Radius or height? Height varies, therefore rate of change is? Area of the base. What is the area of the base? So our rate of change of volume here With respect to what variable is varying? Y is varying now. Okay, so area of the base. And what is, in this case, what's the area of the base? We got a hole now. We got a hole. So the area of the base is that gold region where the thing is growing, right? So we got a hole. So it's going to be what? Pi, our outer squared, minus. That's what we derived last time when the area of the base had a hole in it. So now we got to get these radii, the outer radius and the inner radius, in terms of y, and we've got a rate of change function. So before we get in terms of y, so we just ask, the inner radius, what is the inner radius? Is it x coordinate, y coordinate, a big change in x or a big change in y? The inner radius. Simply the x coordinate. So we can write, that's the inner radius, right?
Yeah. Then the outer
Okay,
radius.
and what's the outer radius? Is it?
It's a constant. It's always 1, yeah.
He's saying it's always 1. Do you agree with that? Do you see that? That the outer radius, no matter what cylinder, what interval we're in, the outer radius is always 1 because this is the line 1. So pi times 1 squared. All right, but what? We needed it in terms of y. Okay, so for practice, I'm going to kind of change the problem up, okay? So all I'm going to do is I'm going to define this function now, f of x, as, I'm going to define it as x cubed over 4. Now that doesn't work with the pictures that you drew because that function goes through 1, 1/4. And these pictures all go through 1, 1. Okay, is it okay though? It's okay. So all I'm doing now is the same situation, but I'm going to change this curve to be f of x equals x cubed over 4. Now, I need x squared in terms of y. How do I get that? How am I going to get that if my f of x was x cubed over 4? So what I'm going to have to do is solve this thing solve it for x. When I solve it for x, then I'll have the x coordinate in terms of y. What will that be? That'll be, can I do 2 steps at once? The cube root of 4y, is it okay? So this area function therefore, or the rate of change becomes pi minus pi times, what's x? X is cube root of 4y. And that's squared. There's my rate of change function. Did I lose you? Ask if I lost you. Yes, please.
Isn't the 1 an x value? Like, is that x equals 1?
Yeah, but that's okay because it's just the number 1, so it's okay because that radius is 1. Doesn't depend on x or y, so it's fine as just 1. We don't have to do anything to it. Is it okay? Yeah. Yeah, even though it's an x value, it's still the radius and it's a constant, so it's fine in terms of y. So there's our rate of change, and then we could write the volume accumulation function. Integral from 0 to y of this thing with t's in it, dt. Will be our volume accumulation function. Yes, please.
And that's just for one disk of it, or the entire thing?
Which? This is the rate of change of volume. It's a function. It's a rate of change function for the volume as y grows.